I'm the field application engineer for the Bussmann division for the Northeast. So I'm based out of Pittsburgh, but I cover the whole state. And as you may have just heard me say, I went to Villanova, so I know that side of the state pretty well. Holds a special place in my heart. So today we're going to talk Fuseology. That's our overcurrent protection fundamentals. And then at the end, we'll talk specifically about some applications for the industrial market. So our agenda, we're going to talk overcurrents and overcurrent protection. We're going to talk about ratings that overcurrent protective devices have. We'll go through the different classes of fuses and each of their applications, and then finally some of those Bussmann solutions specifically for the industrial market. First and foremost, right, the purpose of fuses. Why do we have them, or any overcurrent protection? And it's to help prevent electrical fires and explosions. Right, by protecting from electrical fires and explosions, we protect people from injury due to fires, those fires or explosions. We help protect the equipment itself, and of course, we protect the customer's investment. So with that, we're going to go ahead and talk about overcurrents. What is an overcurrent? An overcurrent is any current in excess of what something is rated for. So that something might be equipment, it might be a conductor, but any amount of current that is in excess of what it's rated for. Could be 1 amp too much, it could be thousands of amps too much. Any amount of excess current makes it an overcurrent condition. Our effects of overcurrents, that's where we get fires, explosions, conductor damage, equipment damage. This is why we want to protect ourselves from overcurrent conditions. The first specific type of overcurrent I want to talk about is an overload. So an overload is operation of equipment in excess of my normal full load rating, where if it were to persist over a sufficient length of time would cause dangerous overheating. So usually it's a smaller, relatively smaller amount of excess current over a long period of time, right? And you can imagine if I've got a conductor in a wall and it has too much current for too long, it heats up, it might start to break down some insulation and cause a fire. So fire is definitely the most common effect of overload. We get that conductor damage, equipment damage, component failure, why we need to protect ourselves from overloads. So this would be sort of my example of a typical circuit, right? I've got my source, I've got my current flowing out to a load and back to my source. So during an overload condition, basically one of two things causes an overload. If you guys see in my top right-hand corner there, I've got I is current. So current is equal to voltage divided by resistance. So what happens in an overload is either the resistance goes down a little bit in my load. So something has happened in my load that's reduced the resistance. And when that resistance goes down, my current is going to go a little bit up, right? Because my voltage is staying constant. So that's one way I can cause an overload. And the other way, I think the most sort of the typical way we think of this would be, in my parents' house growing up, the microwave and the toaster were on the same circuit. And if you ran them both at the same time, about 30 seconds later, the breaker in the basement would trip, right? That's just too much current flowing through, right? Because I have two loads now. I've got too much current flowing through the circuit path. The really, really key thing about an overload current is that current is always flowing within the normal path. So it's still going from my source out to my load and back to my source. It's all still flowing in there. It's just a little too much, and that too much can cause dangerous overheating, and that's why I want to protect myself from it. That is as opposed to a short circuit or a fault. So a short circuit and a fault, those are interchangeable words. For our purposes, the NEC has started in the 2020 version to actually just standardize on using the word fault and fault current. And they say that a fault current is what you get during a short circuit. So they're really all still interchangeable. So when you see short circuit, when you see fault, same thing. And that is an overcurrent resulting from current flowing outside the normal circuit path. These can be hundreds to thousands of amps greater than our normal operating condition, and they can be between phases or between phase and ground, right? So that's how we get a short circuit or a fault condition. My effects of short circuits, these are wild, right? We get some warped bus bars, we get really severe insulation damage, some vaporized conductors, vaporized metals, ionized gas fires and explosions, really, really explosive, literally, effects of some short circuit conditions out there. So my very typical example of a short circuit current here, right? We got the screwdriver going between my two conductors. So when that screwdriver goes between my two conductors, you know, those electrons would normally go out to my load and come back to the source. But, you know, they're lazy. They don't want to go out to that load and do work. They don't have to. Instead, they're going to go ahead and take that shortcut right through the screwdriver. When they do that, they're essentially taking the load completely out of the circuit, right? And so when that load goes out of my circuit, that load is where most of the resistance in my circuit is. You know, not 100%, but like 98% of the resistance in my circuit is typically in that load. So you can imagine I've got that Ohm's law up here in my top right again. If the current is equal to voltage divided by resistance, and that resistance number goes way, way down, right, starts driving towards zero, with that voltage staying constant, that's why I get such high values for that short circuit current, because we are removing so much of the resistance from that circuit path. So short circuit current flowing outside the normal path, really, really high values for that amount of current. Some typical values we might see for a short circuit current. My home receptacle, I usually see between 200 and 500 amps at my home receptacle. Maximum short circuit current values there. At the service of the home, between 2,000 to 10,000 amps. Now that's in a typical, one family dwelling residential environment. If I'm in, multifamily, apartment building in a downtown area, I might see something more like 25,000 there. Light industrial, that's where we see that 65,000, 70,000 amps. Heavy industrial up to 100,000, and then a large city can easily exceed 100,000 and go all the way up to 200,000. New York City and Boston regularly see that 200,000 amp range, so we can see them. I think in Philly we're usually around 100,000, but sometimes we can get up to 150 in the downtown area. So high fault currents, they are definitely prevalent. They're definitely out there, and they're extremely destructive, so we want to make sure we are protecting ourselves from them. So with that, we're going to talk about some of the ratings that overcurrent protective devices have, and kind of what they mean and how we use each of them. So first and foremost, right, the amp rating. The amp rating of a device. So we're going to size that overcurrent protective device based on the load and application. Rule of thumb for any overcurrent protective device is that it is typically 80% rated. So the amp rating is actually 80% rated, which means if it's a 100 amp circuit breaker, it's actually rated to see 80 amps, full load all of the time. Why is it 80% rated? Well, a lot of times it actually has to do with the fact that a conductor is 125% rated. So when you match the breaker to the conductor, it winds up kind of washing out. So that's why we see that 80% rating there. It's actually because of the way that the conductors are sized. You can get 100% rated overcurrent protective devices. So a couple molded case circuit breakers, you can specifically get a 100% rated molded case circuit breaker. It will be more expensive than a regular circuit breaker, but you can get one that's 100% rated. Most insulated case breakers, you can get that 100% rating as well. And then low voltage power breakers, the big guys that go in switchgear, those are usually already 100% rated. For fuses, fuses are actually 100% rated by themselves, but the act of putting them in a holder or a switch, that typically makes them 80% rated. So if you need a 100% rated fuse, you get it in a 100% rated holder or switch. A bolted pressure switch is an example of a 100% rated switch. Why would I use a 100% rated device? Typically, this is in order to save space, right? You can think of something like, say, I need to protect for 425 amps. That would be a 600 amp frame breaker that I would need to use for that. But I could use a 100% rated 400 amp breaker. So depending on, so sometimes I can use that 100% rated 400 amp breaker. That's going to be a lot smaller than that 600 amp frame. And that's why I use the 100% rated devices. I see them used very frequently where that space is a major concern, where it kind of was already designed with one space in mind, and now it's really, really hard to change it. and then we start seeing the 100% rated circuit breakers or switches being used. So next up is voltage rating. So the voltage rating of my overcurrent protective device. And when we talk about overcurrent protective device, so we know we're mostly just talking the circuit breaker or the fuse. My overcurrent protective devices are circuit breakers or fuses. So my overcurrent protective device voltage rating must be equal to or greater than the system voltage. That makes sense, right? So as long as the voltage rating is greater than or equal to the system voltage, I can safely apply it. Circuit breakers have a lot of different voltage ratings that you might see. They've got some slash ratings and straight ratings. Sometimes they have more than one voltage rating on one single component, and the interrupting rating varies depending on which voltage we apply it at. Fuses typically have one of two voltage ratings, 250 volts AC or 600 volts AC, and that is a maximum voltage. So you can apply it anytime up to that maximum voltage. The interrupting rating stays the same the whole time. Your voltage rating might have an AC or a DC rating. You might have both. A lot of fuses have both. A lot of circuit breakers have both, but the interrupting rating is probably going to be different at that DC rating. Really important note about slash voltage ratings. So slash voltage ratings, what a slash voltage rating means when I see it is we're going to take 480/277 as our example here. So what it means when I see it, that first number, that 480 volts, that is the voltage of a three-phase fault that circuit breaker can safely interrupt. So great. All right, I've got 480 volts across three phases. I can safely interrupt a 480 volt fault. Wonderful, great. That 277, that second smaller number, that represents the voltage that a single pole of that breaker can safely interrupt. So if one pole of this breaker sees 277 volt fault, it's going to safely interrupt it. If it sees a fault of 480 volts, though, it's not going to interrupt it. So it's only rated for a fault of that voltage on a single pole. So when do we see a fault on a single pole? That's typically going to be my line to ground fault. So I have to make sure when I apply a slash rated component that my line to ground voltage is not greater than 277 volts. So in a solidly grounded Y system, I can apply slash rated components all day, every day. It's impossible to see more than 277 volts on that line to ground fault in a solidly grounded Y circuit. So I can apply slash rated components all day, every day. In every other type of grounded system, I must use straight rated components because I can see more than 277 volts on a single pole. So circuit breakers, you can get circuit breakers with straight ratings. You can get circuit breakers with slash ratings. Fuses are all straight voltage rated, right? Because you just got that one per pole up to that voltage. So fuses are all straight voltage rated. So that is what the slash voltage rating and the straight voltage rating mean. And it's really, really important we apply these correctly. About 85% of circuits in the United States are going to be solidly grounded Y. That's by far the most common, and therefore you can apply the slash rated components into those. Especially the vast majority of any sort of commercial, institutional type building, residential, those are all going to be solidly grounded Y. Now, unfortunately, it's the industrial market that sees some of those other types of circuits, right? My corner grounded delta, high resistance grounded Y, ungrounded delta, where I can see 480 volts on a single pole. Those are typically going to be in my industrial applications when I see those. So we just want to be careful. Look at that voltage rating, slash rated components, and solidly grounded Y systems only. Next up is interrupting rating. So interrupting rating is the last rating. What an interrupting rating is it's exactly what it sounds like. It's the highest amount of current that it is rated to interrupt, right? So this is applying to that component that does something when there's a short, right? My breaker trips, my fuse opens. It's actually the device that's clearing the fault, right? That's opening up that circuit. So this is how much it can interrupt, right? What the value of that current is, where it can interrupt it. I've got an NEC requirement here, 110.9. And this is basically telling me that all of my interrupting ratings should be greater than or equal to the available fault current. That makes sense, right? Just like our voltage rating should be greater than the system voltage. Same thing with my interrupting rating, greater than or equal to the fault current that it can see. Really, really important note about interrupting rating is that interrupting rating is a self-protection rating only. So what that means is, right, if I'm a breaker and I have a 35,000 interrupting rating, that means me, Mr. Breaker, if I see 35,000 amps, I'm going to trip. I'm going to be okay. But I'm not guaranteeing the protection of anybody around me, right? Those are different types of ratings, meaning that it's protecting other things. The interrupting rating itself applies only to that breaker or only to that fuse. So again, does not mean it's protecting what's around us. And then finally, just as you can see in this example, right, a breaker typically has multiple voltage ratings on it, and the interrupting rating changes depending on what voltage you apply it at. Fuses have a maximum voltage and one interrupting rating, and that one interrupting rating is valid as long as you apply it on a system of that voltage rating or less. So here we have, right, my importance of interrupting rating. Oh, I've got to figure out my a way to get the sound on here because I turned my volume on. I'll have to turn the volume up on my computer real quick here. But this is a test we have here. So we've got, not adequate interrupting rating. We've got 480 volts here, and we've got a 15 amp multi-case circuit breaker. It has a 14 Ka interrupting rating. If you can see on that video on the left, we're basically shorting it right there across the load side terminals. We're showing it right on the load side. And we're going to hit it with 45,000 available fault current. I am going to make sure my volume is on. So this is actually in slow motion right now. This piece, you can see with this piece, I love this part. This part is the, the breaker, it's like the Death Star exploding there in slow motion. So, this breaker, it interrupted the fault, right? There's no current flowing through it anymore, but we do not consider this a safe interruption of the fault. So here's some still photos. You can see pretty much immediately here, it is trying to interrupt that fault current, but there's a little bit too much energy. It's not able to handle all of the current going through it, and that's where we get the boom effect. So in fairness, we're going to do the same thing to a fuse. So the fuse here, we've got 45,000 available, 480 volt fault current, 480 volt system again. So we've got a 60 amp class K5 fuse. The K5 fuse is a much older style fuse, so it only has that 10 Ka interrupting rating, not what we're used to seeing with a lot of fuses, not that high interrupting rating we're used to seeing. So I'm going to go ahead and do this one again. So you can see, right, that one, it interrupted the fault again, but again, not that safe interruption of the fault. So in the still photos here, you can see that hot spot forming, and then just way too much energy. It can't handle it, and we get another big kaboom. So this is the sort of the most boring video we can watch. This is the proper application of some non-indicating fuses. So you get 45,000 available, 480 volts. We've got a 60 amp class J fuse in there. It's got a 300,000 amp interrupting rating. So I'm going to see if I can get this to work right here and actually turn this volume on. And what you'll hear is a beep when the fault current occurred. So hopefully you heard that. There was just a little beep there. Not much happens, right? This is, again, by far the most boring video we can watch on this. But boring is good when it is our own equipment, right? We definitely prefer those first two videos for entertainment value during this presentation, but this is what we want to happen in our equipment and our customers' equipment to make sure that it is protected. So with that, we're going to go ahead and go through some of the different classes of fuses and their applications. So actually, first going to touch a little bit on circuit breakers and how they work, just so that we really understand the difference between fuses and breakers. So right, my overcurrent protective device types, I've got mechanical devices. Most of the time when I think about a mechanical device, I'm going to think about a thermomagnetic circuit breaker. Thermomagnetic circuit breaker is going to have both overload and short circuit protection. Self-protected starters also do that, but we typically think about my thermomagnetic circuit breaker and that mechanical device. Sometimes I've got a motor circuit protector. So a motor circuit protector, a lot of times we see that inside motor control center buckets. It looks just like a breaker, but it's short circuit protection. And then I have overload only devices that I usually pair with that motor circuit protector to make sure I get the short circuit and overload protection, something like an overload relay. On the solid state or thermal devices side, when we talk about fuses, right, we've got fuses that have both overload and short circuit protection. Those are my UL low voltage fuses. And what we, in the industry define as my UL low voltage fuses, they're easily identified because we have the class designation to them. So if you see class RK5, class J, class CC, whatever it is, the class fuse, that means that it is a UL low voltage fuse. It gets that specific designation, and that means it has both overload and short circuit protection. There are some fuses out there that are short circuit protection only. Those are going to be my high speed fuses or my semiconductor fuses. I see those a lot of times protecting drives. So with that, let's talk a little bit about a molded case circuit breaker. So any molded case circuit breaker has a couple common characteristics and components to it. So the first being that molded case frame, right? That's the insulation, and it protects all of the guts inside that breaker. I've got an operating mechanism, right? That operating mechanism, that handle that turns it on and off. I got my contacts in there. My contacts are going to be spring-loaded to separate. So they actually get latched together when the breaker is closed, and then they are spring-loaded to separate. Then I've got some arc extinguishers in there. What those arc extinguishers do is they help me to lengthen and cool the arc. They allow molded case circuit breakers to be a lot smaller than they would have to be otherwise, because most of the time to cool an arc, what we do is we separate the contacts, right? We need to separate those contacts really far. But if I have 65,000 amps at 480 volts, the amount of distance I would have to separate those contacts by would be really, really far in order to get it cool enough to extinguish. So instead we have those arc chutes that help us cool it in a much, much smaller amount of space. And then finally, a trip unit. And that trip unit is going to have some sort of current sensing means, some way to determine that there is an overcurrent condition occurring, and a way to unlatch those contacts so that they'll separate. The tripping conditions of any molded case breaker. So any thermomagnetic circuit breaker is going to trip under overload and short circuit. So that's going to be typical. And then sometimes I can get a specific trip unit that will sense a ground fault and an arcing fault and trip on that as well. So with that, this is sort of my circuit breaker operation, right? So in a normal condition, this is what the inside of my circuit breaker is going to look like. If I look on the bottom right, I got my line coming in, my line power coming in. It's going to go through my spring-loaded contacts, and you'll see that those contacts are latched together, right? So my spring-loaded contacts latched together during my normal state, normal operation. My current's going to go up into that magnetic element, and then it's going to go up and over through the bimetal and out to my load. So normal state, it'll just stay like this, humming along forever, happy. And then what's going to happen during an overload, so remember my overload is a small amount of overcurrent that persists over a long amount of time, is my bimetal is going to do the work here. So that bimetal, what a bimetal is exactly what it sounds like. It's two metals fused together. And what they do is when they heat up, they have different rates of expansion. for when they heat up. And as a result, when they heat up enough, that bimetal bends and it hits into this trip bar. And when it hits the trip bar, that trip bar unlatches my spring-loaded contacts. And so once those spring-loaded contacts are unlatched, that spring will separate the contacts and my overload will be cleared. This is why actually sometimes, right, we can't reset a circuit breaker sometimes immediately after an overload event, and that is because that bimetal is still hot, right? If that bimetal is still hot and it is still bent into that trip bar, I can't reset that circuit breaker yet. I actually have to wait for that bimetal to cool off and straighten back up, and once it straightens, then I'm able to reset the breaker. So now we've gone back to, right, my normal state, so we can take a look at what happens during a short circuit. So hypothetically, during a short circuit, that bimetal would heat up and hit into that trip bar and clear the fault. But that process takes a while, just the amount of time it takes for that bimetal to heat up and hit into that trip bar. And we don't want to wait that long on a short circuit, right? We saw those values of short circuits. They're thousands of amps. And we don't want thousands of amps, persisting for a couple seconds, because that's how long it takes the bimetal to heat up and hit into the trip bar. So that's where this magnetic element comes into play. This magnetic element essentially is, a coiling of that conductor. And when it sees that spike in current, it turns into an electromagnet, and it will pull that trip bar towards it. So when it senses that short circuit, it turns into that magnet and pulls the trip bar towards it. And it pulls the trip bar towards it, right? We're unlatching those spring-loaded contacts. In this case, that spring will separate those contacts, but we'll get an arc, right? Because now we're talking about thousands of amps. So we'll get an arc between those two contacts whenever they try to separate. That arc gets thrown into those arc chutes, right? So those arc chutes will then suck up that arc. It will help to stretch the arc. Stretching it will help cool it. And once it's cooled down and extinguished, then we've cleared the fault. So this is how my circuit breaker is going to operate during a short circuit condition. Fuses, on the other hand, certainly in comparison to breakers, fuses are really simple. They're kind of dumb in comparison. We don't have moving parts on the fault interruption. It's all based on that thermal principle. So some characteristics of my fuses, right? I might have a non-time delay fuse with Bussmann. A lot of times we call this fast-acting, so non-time delay or fast-acting fuses. And then you've got time delay fuses. So time delay fuses work really well as a general purpose fuse, or anytime it's in front of like a motor or a transformer or something that has an inrush current. And then finally, we've got high-speed fuses. And yes, high-speed fuses are different than fast-acting fuses because, of course they are. High-speed fuses are the designation we give to fuses that have short circuit protection only. So they don't have that overload protection. A non-time delay fuse or a fast-acting fuse does have both short circuit and overload protection, as does the time delay fuse. But the high-speed fuse is short circuit protection only. So some key construction features of any fuse. So the first thing they're all going to have, in this example, we have a bladed fuse, but this would be true for a ferrule fuse as well, is we have some sort of physical rejection feature in it. So in this bladed fuse, you can see there's that little notch in the blade. And what that notch in the blade does is it prevents me from installing the wrong fuse in the holder that this fuse would go into, right? It has to line up properly with that notch. Ferrule fuses have some little kind of notch on the top hat there for it as well. And this is a really good feature of fuses, right? It prevents you from installing that incorrect fuse. I always say, right, if you can't install a fuse, installing fuses is never supposed to be a feat of strength. If a fuse is not being properly installed, if it's not going into a holder, it's probably that physical rejection feature doing its job. It's not about adding any more brute force to it. And then finally, we've got that enclosed thermal design, right? So we got that fuse link inside. That's going to operate on a thermal principle. And it's all going to be enclosed in a non-venting design here. We're going to have this arc quenching filler inside. That's basically, we could call it like a silica sand compound, but it's basically just a regular old sand. But we make it sound fancy. as that arc quenching filler. And then finally, of course, we've got factory calibrated replacements, right? So there's no resetting of a fuse, right? We just get a new fuse that is factory calibrated as what I want, and we install that. So we're going to talk about how a dual element time delay fuse operates. The dual element time delay fuse is by far the most common type of fuse. So that's why we're going to talk about how this one works. A dual element time delay fuse, right? It's got two different elements to it. They operate differently on each type of overcurrent condition. So we've got the short circuit element there on the left, and the overload on the right. And so we'll talk about an overload first. So the overload element is actually it is spring loaded and then fused with this fusing alloy to my short circuit element. So with that fusing alloy is there, and what that fusing alloy will do is, during an overcurrent condition, it'll reach a temperature associated with too much current over a specific amount of time. And what it'll do is it'll melt and it'll fracture away from that short circuit element. So that spring, just holding it in tension there, will pull it back, fracture that element totally off. And that's how my overload will be cleared. So I actually do have a moving part in this dual element time delay fuse on an overload. So not on the fault current, but I have a moving part on overload protection in this fuse. And then for a short circuit, what happens is that short circuit element you see on the left there, you can see it's got all those little holes stamped in it. And I have those little restricted sections that are going to connect them. Those are the weak spots on the fuse. And so when they see that spike in current, they're just basically going to instantly vaporize. They're going to vaporize, an arc will form, the arc will burn back on each side, and then that arc quenching filler will get in the middle there and extinguish that arc. And this whole thing in a fuse is going to happen in 4 milliseconds or less between when that arc forms, it sees that short circuit, and it is extinguished. So it happens very, very quickly. The other thing you'll see is with that arc quenching filler, right, it's basically sand. And what happens to sand when sand gets really, really hot, like it would if it was right next to an arc, is it turns into glass, right? Well, in our fuses, we've got to be fancy. So we call it fulgurite, but fulgurite is essentially a glass bead that forms in the middle of where that arc was. So I can actually tell it's kind of cool if you ever open up the fuse after a short circuit. Just cut it open and throw it out. You'll see all those little short circuit elements will be broken up into separate pieces, and then you'll see these little glass beads in there for how it quenched that arc. So that's how my dual element time delay fuse operates under both overload and short circuit. And a dual element time delay fuse is going to be an example of a branch circuit overcurrent protection. So what branch circuit overcurrent protection is this is an NEC definition, and it's the type of protection that can be used anywhere in my system. So it's sort of my top of the line level of protection is branch overcurrent protection. Top of the line level of protection. It means that it can interrupt the full range of overcurrents. So everything from my low level overload all the way up to its interrupting rating, it can safely interrupt that. It's going to have a minimum interrupting rating of 5,000 amps. Typically, we see at least 10, but by definition, a minimum of 5,000 amps interrupting rating. And again, that's sort of that top of the line level of protection can be used anywhere in my power distribution system. These are going to be those UL low voltage fuses, those class fuses. We're going to go through each of those individually here in a second now. When we talk about breakers, those are my UL 489 breakers. And then any insulated case or low voltage power breakers, those are all going to be branch rated devices. And again, those can be applied safely anywhere in my system because it's that top level of protection. So we'll go ahead and talk about each class of fuse. So all of these are going to be those branch rated devices. So my first class of fuse is an RK5 fuse. So the RK5 fuse is the most common fuse. It is the fuse that we make and sell the most of. So it is by far the most common fuse that's out there. The RK5 fuse is the best time delay fuse. So the most amount of time delay that we can get. It is certainly more current limiting than any breaker that is out there. And again, that best time delay, the sizing of the RK5 fuse can typically be the closest to the load on anything with a sort of motor inrush, right? We can size it the closest to the load. It does not have to be as oversized as some other fuses, or a breaker might have to be for it. It can physically replace any Class H or K5 fuse. So Class H and K5 fuses, you'll see here, right, we're in the same amp ranges and the same voltage rating, but much, much higher level of protection that you get out of the RK5 fuse. So we like the RK5 fuse a lot for this reason. And it can replace those H or K5 fuses. It'll actually fit in an H or K5 holder. Whereas the opposite wouldn't be true to that physical rejection, but I can put a better fuse in the older fuse holder. So I can actually put that RK5 fuse in the same holder, so I can upgrade them without having to upgrade, the equipment it's attached to. So my voltage ratings on RK5 fuses, I'm talking either a 250 volt fuse or a 600 volt fuse, and they go up to 600 amps. My FRNR, FRSR, that's the part number I associate with my RK5 fuses here. And then an RK5 fuse can be upgraded to a low peak RK1 fuse. So an RK1 fuse, it's also very, in the same amp range and same voltage rating as that RK5 fuse. So we're talking 250 volts or 600 volts rating there. Up to 600 amps. And the thing with the RK1 fuse is RK1 still has pretty good time delay. When I'm talking about the low peak one, still has pretty good time delay. I have to size it a little bit larger than the RK5 fuse, but not by a lot. 130% as opposed to 125%, so not that much of a difference. And in exchange, I get much, much reduced arc flash hazards. It's a much better current limiting fuse. And so what it does is it really, really helps to reduce my arc flash in comparison to that RK5. So one really, really good way that you can increase your arc flash rating is just by replacing those RK5 fuses with an RK1 fuse. It can also replace those H or K5 and do the same thing. And again, it'll fit in that same holder as the RK5 fuse came in, since it's that upgraded version of the fuse. So really, really great choice here. The LPN or the LPS, that's going to be my part numbers for my RK1 fuse. Next up is that K5 or that H fuse. So you might know this as the NON or the NOS fuse for my Bussmann part number. Same amp range and same voltage rating, that 250 or 600 volt range, up to 600 amps. This is really, really basic level of protection. These are a much older style of fuse. They are not current limiting, nor are they time delay. So they are not time delayed, nor are they current limiting. They are very inexpensive. That is why people tend to still use them today. But I always recommend upgrading a Class H or K5 fuse to at least an RK5, preferably an RK1. Then you'll get the levels of protection that you're used to associating with fuses, that high interrupting rating and that current limitation. You get neither when we talk about a K5 or an H fuse. So anytime if you see some of these fuses out in the wild, people have them installed, I recommend switching those out and replacing them with an RK1. And if somebody comes to you and tries to order that Class H or K5 fuse, right, we want to try and upgrade them then to at least the RK5 fuse. Next up is a Class J fuse. So Class J fuse, we're talking about the same amp range as the RK1 or the RK5, but these are going to all have a 600 volt rating. So we don't have that 250 volt rating. It's only that 600 volt rating for the Class J. The Class J, you're going to have better current limitation. Again, you're going to have some time delay, but you are going to have to size it a little bit larger for some motors. So you're talking 150% now, so a little bit larger than we were talking about for the RK1 or the RK5. But what you get with the Class J fuse is space. So the Class J fuse is a lot smaller than any of those Class R fuses. So we see panel builders like this a lot, right? Those are people who are usually very, very concerned with the amount of space that fuse is going to take up. And even sometimes in our switch gear, our switchboards, right, we want to keep that piece of equipment smaller, so we use a Class J fuse instead of the Class R fuse. Really, really good level of protection here. LPJ fuse, that's my typical fuse I see. And again, we usually, when we get the LPJ, it's because we are willing to pay a little extra to save some space. Next would be a Class CF fuse. Hopefully you're familiar with the Class CF. The Class CF would be the Bussmann cube fuse. The Class CF is identical to Class J in performance. This is still 600 volt max. It only goes up to 400 amps today, but it is the equivalent performance to Class J. So we're still talking the same level of current limitation, the same level of time delay as the Class J. The only thing that makes it different than the Class J is its form factor, right? So part of the definition of a Class J fuse is you have to fit in a Class J holder, and this does not meet that definition. This is our like plug-in fuse. So hopefully you're familiar with this. We've got the examples here where we show it just in the holder. We have it in a switch device as well. This is one of the relatively newer products for Bussmann, along with the switches that it comes in. So we really like this. It goes very, very well for panel builders because you save even more space than you would with that Class J fuse. And then we have it in our fusible panel boards as well. So the next step is Class T, and the Class T is a very interesting fuse. It sort of has a couple very specific applications that it's used in, and you rarely see it outside of those applications. So Class T has very, very good current limitation, and it's very, very small. The vast majority of when I see Class T fuses used, it is for protection of variable frequency drives. So a lot of drives out there specify specifically Class T fuses in front of them. I know ABB drives do, and I think some of the Rockwell drives do as well, although sometimes Rockwell specifies the DFJs. But the Class T fuses a lot of times specified in front of drives. The other thing with Class T fuses is Class T fuses have a 300 volt or 600 volt rating. If you remember, the other ones were 250. So those 300 volt fuses work very, very well in any sort of single phase 277 volt applications. So there's a good amount of single phase 277 volt lighting out there. And we can use the 300 volt fuse here, and that's a lot less expensive than having to go up to a 600 volt fuse in one of the other families. So that's why those are basically where we see those Class T fuses for the most part. Variable frequency drive protection, we see them in some multifamily meter stacks, and then that single phase 277 volt applications, and we do not see them very much outside of that. Class G fuses are kind of the same way. Class G fuses are sort of a very, very niche product. Class G fuses, I see the vast majority of these in data center PDUs. So lots of these in data center PDUs. If you don't work with many data centers, then you probably don't see too many Class G fuses. They are used in a couple of specialty heater applications. It's sort of the only other time we see them, but these are your small guys, 480 volt or 600 volt up to 60 amp, sort of general purpose, basic protection, 100K interrupting rating. They look a lot like Class TC fuses, but they do get a little bit bigger, so they actually get larger in size as you go up in amps. Whereas that Class CC fuse is the same all the way across. So you might not, you can go your whole career without selling a Class G fuse, but I want you to know that we have them if you ever do run into them, and they're typically in very specific applications. So someone is going to want it for a specific reason and ask you for it. Then we've got the Class L fuses. So these are the big guys, right? So up to this point, right, when we're talking Class J, RK1, RK5, right, those only go up to 600 amps. Well, what do we do above 600 amps? Class L. Class L goes from 601 amps up to 6,000 amps. They're all 600 volt rated, 300K interrupting rating. We've got a couple different styles there, but the KRPC, that's our low peak fuse there. That's the most common one that we sell, so that's most likely the one you'd run into. We have some non-time delay ones in there as well. Some are the faster acting. We see these a lot in construction projects where we're trying to coordinate with downstream fuses. They coordinate very, very well with other fuses. And then again, just of course, anytime where we need more than 600 amps, we have to go to the Class L fuse. These are really the only fuse that go up to those really, really high amp ratings. And then last but not least, Class CC fuse. So this is, we went from the biggest guy all the way down to the little guy. Class CC fuse, 600 volt rating all the way across the board. maximum of 30 amps. So we go from a fraction of amps up to 30 amps. We see these a lot in control panels and sometimes in some, motor control centers or industrial machinery. We see them for those control power transformer protection in there. So these are my little guys. I've got 3 different part numbers for these fuses. The FNQR fuse is specific for industrial control transformer protection. So if you got one of those little transformers inside a panel, FNQR is the fuse you want to use for those. KTKR is actually specified sometimes in front of some micro drives, so the much smaller drives. See a KTKR fuse specified there. And then the LPCC is sort of general purpose. Maybe put that in a main switch or branch device, general purpose protection for that LPCC. So here's just kind of a summary, right? All of those low voltage branch circuit fuses, so we can think of it. You can see here, right, my degree of current limitation and my degree of time delay, they are inversely related. And when you think about it, that makes sense, right? If I'm purposely delaying opening, right, purposely putting that time delay in, I'm going to let through more current. So right on here, Class L and Class RK5, they're going to be the most time delay fuses that we have. I do always want to stress, I know they come out low on the current limitation as far as fuses go, but they're still much, much more current limiting than an equivalent breaker. So just keep that in mind when we're looking at this chart. Class RK1, right, more current limiting, but less time delay than the RK5. Class J and CF are equivalent over there, very good current limitation. And then, of course, the Class G, Class T, and Class CC, those are my sort of top level of current limitations they can get. Just remember that Class K5, that H, those are that not time delay at all. They're not current limiting. They're kind of outside this whole category, and we always want to try to upgrade those, to an RK1 fuse if we can. So those were all my branch-rated overcurrent protective devices, right? I said those could be used anywhere in my system because they provide that branch level of protection. The other types of fuses and other type of protective device that we can get is going to be a supplementary overcurrent protective device. It provides very limited overcurrent protection. It should only be used where you already have branch protection. There's no minimum interrupting ratings or voltage ratings. These are generally limited to control circuits only. So not just control panels, but the control circuits within the control panels. So these would be my UL 1077 supplementary protectors right there. So they look a lot like those miniature circuit breakers that are branch rated, the UL 489 ones, but they don't have the fins on the end of them. That's how you can usually tell the 1077 versus the 489. And then it would be the midget fuses or glass fuses. Those are the supplemental fuses, that we see a lot. And a lot of times, again, we see those in our control circuits where the limited protection is all we need. So that's it for all of my different types of fuses. So I'm going to talk now just for a minute here about some Bussmann products specific for the industrial market. The first one is going to be a low peak fuse upgrade. Hopefully you're familiar with this program, but the whole idea of the upgrade, the low peak fuse upgrade, is that Class RK1 fuses, the dual element time delay, so those are the LPNs and the LPSs, they can replace any renewable Class H or K5, Class RK1, or Class RK5 fuse that is installed in a facility. So they'll fit in all the same holders, right? So you don't have to change out holders and switches to put these in. They'll fit in all of those. And as a result, what you get is enhanced safety, right? Because the Class RK1 fuse is going to have the best arc flash protection you can typically get out of any of those. You'll get improved reliability, so you get higher interrupting ratings. Sometimes you can get type 2 no damage protection, and what that actually means is that whatever it's protecting, it can be used again after a short circuit. That is not necessarily the case with every sort of level of protection, so you get that higher interrupting rating as compared to that K5 or that H fuse, and probably better protection for your actual equipment. And a much more simplified inventory, so you can reduce your SKUs by 33%, sometimes even more, depending on what the state of an inventory room currently looks like. So you can reduce literally just the number of SKUs you have in your inventory by a significant amount by upgrading them all to this RK1 fuse. So how it works, step 1 of the program is to an audit of the inventory in a facility. You also, typically want to take a look at the fuses that are installed in the field, just so you're not forgetting any there, and you make sure you upgrade those as well. Step 2, you send that list to Bussmann. We analyze it. We usually get it back to you within a week, and you get this detailed report. And what's in this detailed report is all of the fuses that you have and what you could use instead, the simplified inventory version of that list, which has converted a lot of them to that low peak RK1 fuse. We give you sort of an estimated cost savings associated with that, and then that amount of inventory reduction. And then step 3 is to upgrade, right? Place that PO to replace all of those items in your storeroom. A lot of times we'll work out something so we actually buy back the old inventory. You get like a credit towards that first order because we'll buy back that inventory to get all of those Bussmann fuses in. So this is a really, really great program. It's good for a couple of reasons. One, it's just nice to get one big order for fuses, selling them one at a time. Or 3 at a time usually. It's just a couple bucks here and there, so it's nice to get one big order. And the other thing is then they've got Bussmann fuses in their inventory. They know that they bought them from you. So anytime they go to replace a fuse, they're going to replace that fuse that's in there, and they're going to get it, typically where they got it from before. So it locks Bussmann and you, into place as where you're going to go get that replacement fuse from. So it keeps on giving as far as that those orders go. One big order and then all of the replacement orders afterwards. You are far, far more likely to get once you've done this low peak upgrade program. So that's the first one. And the second thing I just want to talk about is this Eaton Bussmann arc flash relay. So the Eaton Bussmann arc flash relay, this is another arc flash mitigation device that we have very recently come out with. The really good thing about this is that it is great for installation in new equipment, and is also fantastic for integration into existing equipment. It's really good when we have upstream fuses or upstream breakers, so it is agnostic to what that upstream device is. And how it works, it's going to measure light and current by doing both. It's going to eliminate any sort of nuisance operation for this, so it's really sensitive to being able to tell when an actual arc event is occurring versus sort of normal operation. And then we've got this choice of fiber optic loop or wired point sensors. This is probably more specific information than I would put for a general overview of this device, but I include it here because anytime I have presented this to a customer, their first question, like every single time, has been, is it a fiber optic loop or is it wired point? So people out there, feel very strongly about fiber optic loop versus wire point sensors. Some really like one and hate the other. So it's just really important that we could say, yes, it could be either. Whichever one you want, we can do that because, again, people tend to have very strong opinions as to which one is better. So we can do either. And this is what it looks like when it's installed. So you can see those are the light sensors that we put in there. So you can imagine how this would be very, very easy to install into existing equipment, right? You just take some of that empty space that's in there and install this, and then that relay goes right on the door. Again, doesn't take up a whole lot of space. So really, really easy to install in both new and existing equipment, just as a result of sort of its very small and modular design here. So how it works is we've got those light sensors that we saw installed, and then we've got some CTs. And what's very important is that we have both of those, because both of those will work together, and this whole arc flash relay system can actually verify that an arc event has occurred because it's going to use both of those inputs. If we only use one of those inputs, you might get some sort of nuisance operation, but by using both, we can tell, an arc event, something is actually happening here. And it can do all of this in less than 4 milliseconds, which is, really, really fast, which is how quickly you want something to operate during an arc event. So once it decides an arc event is occurring, it's going to send 2 signals. One's going to go to an arc quenching device. What this arc quenching device is going to do is it's going to commutate the arc. That basically means it's going to redirect the arc to somewhere where it can be contained, so that it is not blowing out to a person who might be in front of that equipment. It's going to redirect it somewhere safer and then contain it there. And then it's also going to send a signal to trip the upstream device, but could be a fuse, could be a breaker, whatever it is you want to open the upstream device as well. That act is a slower act just in general by some mechanical features. So that's why we want to, in the meantime, we try to quench that arc with that device and clear the fault. And that's generally how it operates, again, really, really quickly. The applications and markets we see for this, so low voltage or medium voltage switchboards, switchgear, and MCCs. So that's definitely where we would see something like this being installed. Our markets, industrial, commercial or institutional infrastructure, oil and gas utility, really anyone who is interested in lowering their arc flash hazards. So anybody who comes to you saying, what solutions do you have to reduce my arc flash? This is, I genuinely think this is one of the best solutions out there for existing equipment. It doesn't really require that much modification to your equipment. You don't have to shut it down for that long to install. It's so easy to install. There's not that much to it, that you don't have to do a shutdown for a week or something in order to install it. So it's a really, really great solution out there and, relatively inexpensive compared to some of the other solutions too. So with that, I'm just going to wrap it up here, right? Reminder, how to choose the right fuse for the job. So for new equipment and installations, we always want to try and specify and install the most current limiting fuse, the Class J or the CF. That's sort of the most upgraded fuse. We want to try and get them to use that. We never recommend that Class H fuse, right? We always want to try to upgrade that to Class RK1. We can upgrade them to our RK5 too, but at least, Class RK1 would be the goal. And then, of course, we want to size to keep fuses as close to the load as we can, right? That'll help us reduce the cost and improve the protection. With existing equipment, we want to replace any non-current limiting fuses with current limiting fuses. So we see any of those white Class H K5 fuses out there, we always want to try and replace those, upgrade them to those low peak fuses, do that low peak upgrade program maybe for an entire facility. And then anytime you're trying to reduce arc flash hazards, that Eaton Bussmann arc flash relay system is a really great way to go. So with that, all I have for now. If anybody has any questions, please feel free to ask them now. You can also, shoot me or Matt an email on that. But I really want to thank you all for joining today, and I hope everyone stays safe out there.